Hello, everyone. We're going to go ahead and go over section 2.3. So using Venn diagrams to study set operations. Now in our last section, we studied set operations, but now we're going to use Venn diagrams to give them visual aspects. So as an overview, have you ever wanted to post a picture to Twitter and Instagram, but maybe not Facebook? Maybe it's a picture you want your friends to see, but not all your family members on Facebook. So this would be a kind of relationship between groups that you could represent with a Venn diagram. Maybe this picture is, good enough to show your friends, but maybe you don't want your family to see it, so that would be excluded from like the set of your family. So as another example, we have a picture here. We have three different sets. We have starting a fight, petting a dog, and consoling a child. We see that certain sets share certain elements. So between starting a fight and petting a dog, you can ask the question, do you want to go outside? Depending on kind of how you say it, it could be included in either one of those sets. Between petting a dog and consoling a child, you can make some shushing noises. Between starting a fight and consoling a child, do you want to call your mommy? So different tone of that can change the context. And between starting a fight, petting a dog, and consoling a child, you can always include the phrase, hey, buddy. So that could be something that could be said in any one of these different scenarios. So that was a silly example of a Venn diagram and how we can visualize certain aspects between different sets. So illustrating a set statement with a Venn diagram. So we have a couple steps for illustrating a set statement with a Venn diagram. With step one, first you draw a diagram for the sets and number each region with Roman numerals. Roman numerals are really up to you. They're just the most commonly used because when we write things in each of these sets, sometimes they are numbers, and if you number them, you may end up getting confused about which set was labeled which. So we use Roman numerals to label each set and each region. Step two, using those numerals, list the regions described by each set. So you would list them probably on the side. Step three, find the set of numerals that correspond to the set given in the set statement. So figure out which regions correspond to the correct area based on your set statement. Step four, shade that area corresponding to the set of numerals you found in step three, and your answer would be whatever elements are covered in your shaded region. So we'll do a real example for this, but this is what we'll do to illustrate a set statement with a Venn diagram. So we see our image here. We have set A, set B, and then our universal set. So in everything that is just A is in region one. So when we list the regions described by that, we would say region one, just A. Region two would be A and B. So the intersection, what's in both A and B. Region three would be elements only in B. And region four would be everything outside of A and B and both. So whatever's still in the universal set, but not contained within A or B or both. So those are the different regions that we have. So when we shade them in, we know kind of what we're talking about. And then we can just quickly identify the elements left in those sets. So let's go ahead and we have here our description of our regions. So region one represents the elements in A that are not in B. Region two is in both A and B. Region three is what is in B and not A. And region four is all the elements in the universal set that are not in A or B. So here we do have the description of those regions that I had described on the previous slide. All right, okay. So now for the Venn diagram below, what option corresponds to A minus B? So we have our set operations now. We're using a Venn diagram to describe that. So for the Venn diagram that we have right here, we're asking which option corresponds to A minus B. This is our set difference. This is when we're talking about what is in set A that is not at all in set B. If we look at our picture, A is the set that the house is on fire. B is the set that you are out of coffee. What is in both is that you are leaving the house immediately. So if your house is on fire, you're leaving the house immediately. And if you're out of coffee, you're leaving the house immediately. Universal set would just be everything that is not A or B. So if we have the set difference, A minus B, we're saying what is only in set A. That's really what A minus B means. What is in set A that is not found anywhere in set B? And what is only found in set A minus what's also in B is the only region of A minus the part that they share. And that would be the house is on fire. That would be our answer for that one. So we can use our imagery here to kind of reason out which is which and what would be our correct answer. So, all right. Now we have A intersect B. Remember, A intersect B is the intersection what is in both. It's the overlapping part. The overlapping part is this part in the middle, which is leaving the house immediately. So the option that corresponds to A intersects B would be leaving the house immediately. That's the part where they overlap. Then for a Venn diagram below, what option corresponds to A union B? A union B is everything. Everything in A, everything in B, and everything in both. Meaning that the house is on fire, you are out of coffee, and you are leaving the house immediately. So all of these things are true. Your house is on fire, you're out of coffee, you're leaving the house immediately. So this is a little bit of a sillier way, but still a great way that we can see how this kind of works with visual representations. So now we can go on to illustrating a set statement with a Venn diagram with 3 regions. 3 regions is always going to be more difficult because you have extra sets. That produces a lot of extra overlapping parts. It's not just the one center overlapping part. So illustrating a set statement with a Venn diagram. Say region 1, and by the way, the steps are the same with illustrating a set statement with 2 sets for Venn diagrams. But here we have our regions breaking down. So we have region 1 represents the elements in set A that are not in sets B or C. So if we look here, we have region 1. This is what is in A, but not in B or C. So none of the overlapping parts. It's only what is in A. Region 2 represents the elements in A and B, but not C. So just this overlapping chunk here. Region 3 represents the elements in B that are not in sets A or C, so only in B. Then we have region 4, this one right here, represents the elements in A and C, but not in B. So this right here. Region 5 is the elements in all 3 sets, A, B, and C. What is in all 3? Then we have region 6, represents the elements in both sets B and C, but not in A, so excluding A, but just B and C. Region 7 is what is in C, but not A or B, so only in C. And region 8 is our final region. It represents the elements in the universal set U that are not in any of the sets A, B, or C, or any of the overlapping intersection points. So that's what all of these regions are going to indicate. So when we go ahead and we figure out values based on certain problems, we'll be able to break these down. So let's go ahead and do an example. Now we have if U is equal to Cleveland, Indianapolis, Chicago, Des Moines, Detroit, New York, Los Angeles, Seattle, Los Angeles, I said it twice, Los Angeles, San Diego, Phoenix, and Boston, then we have certain sets. A is equal to the set of Cleveland, Indianapolis, Chicago, Des Moines, Detroit. B is New York, Los Angeles, Chicago, Detroit. And C is Seattle, Los Angeles, and San Diego. We're going to find the following functions using Venn diagrams. If this looks familiar, it should. It was our example from our last section, section 2.2. So this is the exact same example. We only have different questions now, and we're going to use different We're going to use our Venn diagrams to try to answer them. So we have 2 that we're doing. Part A is A complement intersect C complement. So we'll need to know what is A complement and what is C complement. Then B, we'll have B minus C minus A. So B minus C will be subtracting any elements from C from the set B, minus A, then taking that answer and subtracting any elements that are also in A. So we have intersection with apostrophe or our complements here, and then we also have our set difference. So we're trying out some new problems, but the sets are the same as our last section. And we'll use Venn diagrams. So let's go ahead and head over to our notes to work this out. So we can draw out our Venn diagrams and indicate which elements belong in which regions by drawing those out. So we've drawn out our universal set, the box. We've drawn out our set A, our set B, and our set C. Then we've written which elements belong in each. So we have in set A, we said there was Cleveland, Indianapolis, and Des Moines, only in set A. A and B shared Chicago and Detroit. B has New York. C and B share Los Angeles. C has Seattle and San Diego. And the universal set has Phoenix and Boston. And if we look, there is actually no element that A, B, and C all share. So we've written in the empty set, meaning that there's nothing there. And then we also have that A and C also don't share any elements at all. So I wrote the empty set as well. You can also just write nothing to indicate they don't share any actual elements. But I drew those in just for representative purposes. So what we have here is we have A complement intersect C complement. So what we're going to do is we're going to do some shading. So let's go ahead, get out our highlighter here. And what we're going to do is we're going to shade in A complement. We're just going to shade everything that is considered A complement, which is everything but the set A. So we're going to go ahead and shade some stuff. So we shade, we're avoiding A. We shade everywhere else though. Everywhere else gets shaded. Everything in the shaded regions would be considered A complement. But we're intersecting this with C complement. So when we intersect it, what we're finding in the end is the regions that they both share. The shaded regions they both share. And now to shade in C complement, we're going to shade in green. So everything except C. So everything except C gets shaded in. So we definitely have some interesting shaded regions in here, but really what we're looking for is anything shaded red and green is our answer. So we're looking for answer is anything shaded red and green. So it has to be both. So when we look and we start identifying parts that are shaded in red and green, both, if we look at A, it's shaded green, and C, it's shaded red, so both of those don't count because they only have one shaded area. And then their complement or their intersections also don't count, but there's nothing there anyway. So the parts now we're looking at are Phoenix and Boston, and also New York. Those are the only elements that are shaded both red and green. So for our final answer here, for the intersection of A complement and C complement, we would say that this is the set Phoenix, Boston, and New York. And that would be our answer. So that ends up being our answer. So when we use shading, we're looking for like the overlapping colors, things like that. So it gives us a much better visual than if we just wrote it out or like slashed out elements or anything like that. So this gives us a really good visual. All right, that was part A. We're essentially going to do something very similar for B. When we go down to B, we have the same setup here. We have the same Venn diagram, but now we're shading things differently. So our very first part that we have here is B minus C. So B minus C is going to indicate all of B, but subtracting anything that it shares with C. So we have all of set B. This is all set B right here. So that's all set B. Now what we want to do is we're subtracting C, meaning we're taking away anything that B shares with C. So any overlapping part is now going to be erased. So it ends up looking like this. So we've erased everything that was also contained in C. Then we're saying minus A. So we're taking this answer, the current shaded region that we have, and we're subtracting anything that is also shared in set A. So that becomes erasing this section as well. So now we've taken away everything that is also contained in set A. So the only answer left is what is only in B, which is New York. So the answer would be the set of the single element New York. And that would be our answer there. So we see how coloring in these sections and whatnot, this can help us give a really good visual representation. It can help us a lot with answering our questions. So it's always going to be very helpful to draw yourself a Venn diagram if it is applicable. So definitely always consider drawing Venn diagrams and trying to figure out relationships or set operations. It can be a really, really great tool. All right, let's go over back to our lecture. All right, so we wrapped up this example. And moving on, we have something called De Morgan's Law. So De Morgan's Law states that even if two set statements look different, they can actually be the same. De Morgan's Law is one of those cases and can account for situations very similar to this. De Morgan's Law is a little bit like the distributive property with set operations. So we say De Morgan's Law for any two sets, A and B, if you have A union B complement, that's the same thing as saying A complement intersect B complement. So we see here we kind of distributed the complement, and when the complement went to the operation switched. It changed from union to intersection. And the same thing happens in the opposite direction. A intersect B complement is the same thing as A complement union B complement. So the complement applies to both sets and flips the operation. And these things are the same. When we represent those within our Venn diagrams, they will end up with the same shaded regions. They end up with the same answers. So over here we have A intersect B complement. A intersect B is the chunk in the middle, the shared part. But it's everything other than that because it's the complement. So it would be this, all the green shaded region is A intersect B complement. And the green shaded region is actually the same thing as A complement and union B complement. So everything other than A and everything other than B, which ends up leaving out what they share. So these statements are the same. They would have the same shaded regions. So either one is right. So if you like one version better than the other, you can always use them interchangeably now. Same thing over here. If you have A union B complement, that means that you have A and B and both, everything other than that. So the green region would be that part. Then you have A complement intersect B complement. So everything other than A, in addition, everything other than B. So what is ever in both of those. So everything else. So these shaded regions indicate that these statements are all going to be the same. So you can now use these interchangeably whenever you would like. Gives you a better idea. Maybe you found one thing and you can kind of match it better than with the other. But De Morgan's law is an example where two set statements that look different are actually the same. So let's take a couple looks at these. So for the Venn diagram below, what option would we say corresponds to A union B complement? So A union B is everything essentially here. It would be drunk in love and drunk in love. So it's everything. So each set and what they contain. But we're saying it's not that. We don't quite know what our universal statement is, but we can just kind of add in the word not in this case. So if A union B is drunk in love and drunk in love, not that would be not drunk, not in love, and not drunk in love. Something like sober, hateful, and rage. So this would be kind of a funny example, but we see these kinds of things when we have like unions and intersections with complements using De Morgan's law. So we can kind of piece that out ourselves. So what if we go over to A complement intersects B complement? This is an example of De Morgan's law. Our last example was A union B complement, and we're saying that De Morgan's law tells us this answer should be the same. You can shade in your regions to verify, but this would be A complement, everything other than drunk, and B complement, everything other than in love, and then the combination of those two, which once again creates not drunk, not in love, not drunk in love, sober, hateful, and rage. So that's an example of De Morgan's law. So even though they look different, they really are the same set or the same answers. So moving on from that, we have the cardinal number of a union. We learned about cardinality or the cardinal number of a set a while back, but now we can find the cardinal number of a union. So if n of A represents the cardinal number of set A, then for any two finite sets A and B, we would have the cardinal number of A union B is equal to the cardinal number of A plus the cardinal number of B minus the cardinal number of A intersect B. And kind of how this breaks down is you have the number of elements in sets A and B, so the union of A and B and both really, is equal to the number of elements in set A plus the number of elements in set B minus the number of elements in both. How this is calculated is because if you take the number of elements in set A and the number of elements in set B, you're kind of counting what they share twice. You're overlapping them and you would end up counting twice. So for example, in the picture that we're given here on the side, set A is the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. The elements in B are 10, 11, 12, 6, 7, 8, 9. So when you would count those up, I would say, okay, my elements in A are 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 elements in set A. In B, I have 1, 2, 3, 4, 5, 6, 7. 7 elements in set B. But if I really look, all the elements that are listed, there's really 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's only 12 actual elements. But if I do 9 plus 7, that ends up being 16, and that's not the same number. It's 16 because we counted 6, 7, 8, 9 twice. So when we find the cardinal number of a union, we have to subtract one set of what they share because technically we added it twice. You only want to add it once, so you take one of those sets off. So that's how we end up figuring out the cardinal number of a union. So let's go ahead and do an example. For example, we say 112 doctors are helped by RNs, 83 doctors are helped by LPNs, and 21 of all those doctors are helped by both. How many doctors had at least one type of nurse? So we're going to use a Venn diagram and represent this situation and then answer our question. All right, so here's our question again. We're saying 112 doctors are helped by RNs, 83 doctors are helped by LPNs, and 21 of all those doctors are helped by both. So how many doctors have at least one type of nurse? So within our question here, we're seeing that we have some different situations. We're saying 112 doctors are helped by RNs, meaning that this entire shaded region in here, the total number of doctors being held by RNs is 112. It's 112 in that entire circle. So we don't really count what's in both quite yet. Then same thing here. 83 doctors are held by LPNs. So that would be everything in this shaded region. And this number would be 83. So we don't quite have the both part, but then it does tell us 21 of all of those doctors are helped by both. So I already have my 112 and I have 83, but now I'm saying 21 of both of these numbers are considered helped by both. So when I have 112 and 83, it's really tempting to put 112 on the red side, 83 on the blue side, and put 21 in the middle. But really what I'm saying is 21 of both of these numbers are technically both. So what we have to do is we end up subtracting. So let's go ahead, erase, erase what we have here. So we're going to erase those. What we know from the get-go, 21 are helped by both. 21 is the number that goes in the center in the overlapping part. 21 goes there. Now we're saying 112 doctors are helped by RNs. 21 of them are also helped by LPNs. So our value here in RN would be 112 minus the 21. So we subtract 21 from 112, and this creates 91. So 91 people are helped by RNs, or doctors are helped by RNs. Then we also have 83 doctors are helped by LPNs. We're going to do the same thing over there. We'll take 83, subtract 21. This comes out to 62. So really what we have here is 91 doctors are helped by RNs, 62 doctors are helped by LPNs, and 21 are done by both. So when we have the question, how many doctors had at least one type of nurse, at least means including two, one and also two, or one or two. So we would consider all the values, RN plus LPN plus both. Well, we can write in both there, both. So at least one type of nurse would be 91 plus 21 plus 62. We add up those numbers and we get 174 doctors. So our answer would be 174 doctors. That was using our Venn diagram. What we're going to do now is use our cardinality equation that we just learned. So this is using a Venn diagram. I want to show you both ways so you get a little bit more practice with Venn diagrams, but also you learn the cardinality equation. The cardinality equation we said was the number of elements in A union B would be the number of elements in A plus the number of elements in B minus the number of elements in both A intersect B. So for us, the number of people helped by RNs was 112. The number of doctors helped by LPNs were 83. And the number of people helped by both, or the number of doctors helped by both, would be 21. So really, the number of elements or the number of nurses helped by those doctors is 112 plus 83 minus 21. So we go into our calculators. 112 plus 83 comes out to 195 minus 21 equals 174 doctors. So there we have it. So there we have the equation that we learned for the cardinality of a union. We also did it with a Venn diagram. We saw kind of the picture. We saw how to calculate that Venn diagram. So when calculating a Venn diagram, these are the types of steps that you want to make sure to take. But when it comes to finding the cardinality of a union, you can use this formula as well. Formula was obviously a little shorter, definitely. So using the formula can definitely be quicker in that sense. So, all right, let's go ahead and go on over back to our lecture. All right, that was our example, and that wraps up section 2.3. So in summary, in section 2.3, we learned how to illustrate set statements involving two sets of Venn diagrams, how to illustrate set statements involving three sets of Venn diagrams, using De Morgan's laws, using Venn diagrams to decide if two sets are equal, and using the formula to find the cardinality of the union of two sets. So that wraps up section 2.3. I'll see you in the next one.